Okie dokie. Talk about this. Here's a table. Here's a pulley. Here is some mass. Call that M1.
What's that, people?
Going around a pulley. It's a really bad picture, but you get the point. Here's another mass. M2. This is a pulley on a table. Let's go ahead and label everything that's happening here. First things first, Alexa, just name some force, some direction, some anything. What's going to happen with a system like this?
There's gravity.
Gravity, yes, gravity. And how do you want to label? Which one? M1 or M2? Which gravity do you want to talk about?
I guess M1.
M1. So you're going to have force of gravity down. Very good. Force of gravity down. I'm just going to keep on going around the room until we label everything. All right, Kaylin. Some other force.
Tension.
Tension, yes, for which block?
We'll go
M2.
to going up.
Tension pointing towards the pulley. Always pointing towards the pulley. Very good. All right, now Greg, something else.
90-degree angle.
Hmm?
Because it's the edge of the table, it's a 90-degree angle.
Yeah, 90-degree angle, very good. But we don't really necessarily have to worry about that because it's on the pulley. This pulley, in a perfect world, redirects the force without worrying about an angle.
Okay.
Yeah. So go one more.
The force of gravity on M2 down.
Yes. Yeah. So gravity on M2 down. Alexa, back to you.
The tension on the M1.
Yep. Caleb. There's still more happening here. Let me give you a hint. This block is falling. All right? So what is this block doing?
Forward.
It's sliding across the table.
Oh, which?
Friction.
Across the table.
Yep. So there's some sort of friction force pointed that way. We'll call it FK. It's sliding. Friction force pointed that way. Greg, what other force? There's some other stuff happening here. Yeah, you do. If there's some force of gravity on this mass right here,
The table's flying force up.
normal force, yep. And knew it. And Alexa, finally, there's one last thing happening in here. We talked about it with the Atwood machines yesterday, but these aren't perfect Atwood machines. Like, these aren't perfect pulleys, right? They're plastic, cheap, so they're gonna have what?
The pulley itself has friction?
Yes, there's some sort of mu within the pulley, right? If it was a perfect pulley, you'd be a trillionaire. So figure out how to do that. With like zero energy loss within a pulley system, gosh, you can make so much money off of that. Wow. Just thinking about it. Okay, but yeah, this is what it looks like. All right, so this is a pulley on the table. Not as complex as it seems, though. All right, for our purposes, each pulley that we deal with, and that I'm going to give you, is frictionless. Okay. I still want you to know that the friction's there, but for our purposes, it's frictionless. When you get to college and you follow my direct path and you say, I want to be just like Mr. Spear, and you take this class, classical dynamics, you'll learn this, and you'll have to take into account the friction of the pulley. But you won't even do it this way. You'll say kinetic energy is equal to potential energy, and you'll find it like that. But you don't do that. All right. So there's obviously some sort of motion right here. All right. And let's, for instance, say, right now we have a block of ice. M1 is a block of ice sitting on an oil slick on top of a super smooth metal table. So zero friction. Zero friction. We can write the acceleration of our mass 2, the mass that's falling down here, we can write it as this. Say, okay, A is equal to gravity times mass 2 over M1 plus M2. All right? So our acceleration of this entire system right here is a proportion of the weight. Remember, gravity times mass is the weight. It's a proportion of the weight of the mass divided by the total weight of the system, or the total mass of the system. So that's how we find the acceleration like that. So let's do a quick example with this one. I'm going to say that mass 2 has 10 kilograms and mass 1 has 15 kilograms. Let's do that. You say, okay, A is equal to 9.8 times 10 over 25. So 98 divided by 25. Type that into your Excel sheet.
No.
You got it?
396.
392.
2. Well,
I hate you so much, Kevin.
That was pretty good mental math, though. Well, what's your trick for that?
so I did just M2 over M1 plus M2, so I got a 2/5, and then I multiplied to 9.8, 19.6, and then I just divided by 5.
Neat. So 3.92 meters per second squared. That's our acceleration for this system with no friction in it. But if we have friction, right?
Yeah.
We don't live in a perfect world. We have friction. So how do we solve that? Let me erase this. You just add one thing onto it. And Alexa, you know what to do. There's 3 parts to this, all right? There's 3 things that we're missing right here. What's one of the 3 things that we have to have in that?
The M1.
Yes. Very good. Simple. M1. All right, and I'm going to make this simpler. I'm going to pull this G and say, okay, G times M2. Now, Kaylin, what else do you think has to be taken into account when we talk about the motion of M1? What has to be taken into account the motion of M1 sliding? Hmm?
Like normal force.
Yeah, you're on the right track. Okay, think about the normal force, but not the normal force exactly. It's the normal force times
Gravity.
gravity's in there. I'll give you that one. Greg, do you think you know? Friction coefficient, yeah. It's the friction coefficient. So this is how you would find and solve for some sort of friction, right? So say we have the same value for this, but now we have some sort of constant. Now this is a wooden block on sandpaper. So we have mu is equal to 0.4. Now we can solve that this way, right? We just plug in everything we know and we'll find the acceleration of its system. So how do we do that? A equal to 9.8 times 10 minus 15 times 9.8, 0.4, all over 25. Remember, 10 plus 5, 25. All right. You say, okay, A is equal to 98 minus, what is that, 58 point something?
58.8.
58.8, yep. 58.8 over 25. And we get a final acceleration that's equal to, I don't want to do it on calculator.
1.57.
0.57?
1.57.
1.57. That seems right. Yeah. So that's how you would do these little like table and a pulley question. These are really good questions. These are going to be on your test. It's going to be exactly like this. And the way it's formulated is I'm going to give you a question. I want you to draw a picture like this and label it like I did, right? So gravity, tension, friction, normal force, gravity, tension, all that stuff for both of those things. So here is a quick practice problem, or practice questions. There we go. We need 3 of them. All right, print. Let me turn this off.